So first I want to spend some time talking about the exam. And before I do so, just the numbers. The class actually did fine overall. Here we go. So again, these are out of 60. The average was 42, which is exactly 70%, but the median score was 46.5, which was in the upper 70% range. So, you know, that's pretty typical. If you're trying to estimate your grade based on just the one exam, then approximately 90% is an A, 80% is a B, etc. So what is that? 54 is an A, 48 is a B, 42 is a C, etc., etc. There was a very large range. The high score was 60 out of 60, so that's always nice to see. The low score was 8. And there were actually several students who scored down in the 8 to 20 range, which is very low not passing. So I'm a little concerned about those students. You know, if you scored just barely below the 60% range, you know, technically it's not passing, but I'm not too worried. You've got 2 more exams and homework scores. So hopefully you'll be able to improve over the next several weeks. So the first problem was a Otto cycle problem. You know, we generally like to show Otto cycles on a PV diagram. Okay, so we understand that we have isentropic compression, we have constant volume heat input, we have isentropic expansion, we have constant volume heat rejection. So probably the first thing to do is solve the problem in the order that I've described. So first we want to find R, the compression ratio. Now you're given the volume at the end of the compression stroke. So basically you're given V2, which is the same as V3. So 5.66 inches cubed. So that's been given in the problem. We just have to use our ideal gas equation of state to find V1. So without actually plugging in the numbers, we end up with 38.944 cubic inches. And then we could just take the ratio of these two terms, V1 over V2, and we get 6.881. So that's the first thing you want to do. By the way, if you use a value of R from the air tables, actually it's from table A1 and A2, if you use R with the units of PSIA foot cubed per pound mass degree R, then you don't have any conversions. If you use a different value of R, or if you use a universal gas constant, and then divide it by the molar mass, you know, you'd still have to go through some conversion factors. But nonetheless, you know, if you missed something on your exam, if you didn't have the right numbers, I put little red marks on there, so it should be pretty clear what I saw was missing. All right, so this is the first thing we do. We find R. Now we have to start going through the cycle itself. So we're going to start at T1. So T1 was given to you. It says at the beginning of the compression stroke. So T1 is 540. So at this particular temperature, we have to go into table A17, really it's A17E with the proper units, and we find VR1 of 144.32 and U1 of 92.04 BTUs per pound. Okay. Now we would recognize that our compression ratio is also equal to the ratio of the relative specific volumes. So having VR1, we can just plug in above, and we get VR2 of 20.975. And now that we have VR2, well, we go back into table A17E and look up the internal energy, which we're certainly going to need later. So 199.11 BTUs per pound. And we'll also look up the temperature, which is 1146.4 Rankine. Okay, so this will have to be done by interpolation on this particular table. And then you've also been asked to find the pressure at point 2. So why don't we also just use the ideal gas equation of state for that. We used it earlier to find volume. Let's use it at point 2 to find pressure. And we get 207.4 psia. Okay, so I mean, there are other ways to do this. You could use relative pressures to go from point 1 to point 2. It is isentropic after all, but this is probably the easiest way to find the pressure at point 2. All right, so now we have temperature and pressure at point 2, which is the end of our compression, and now we can move on to part C of the problem. And here we would note that the heat input is just U3 minus U2, and that's given as 431 BTUs per pound. And this is just U3 minus U2. So we have U2 from above, so we get U3 as 630.11 BTUs per pound. And now that we have this, well, now we can go back into our table, this time at U3, and we can look up the temperature. So T3 is almost exactly 3200 Rankine. In fact, that's why I picked such an odd number for the heat input, just so that we would specifically be able to go right into the table at U3, no interpolation required, and just read out the data directly. We also find that VR3 is 0.955 at this particular point. We're also asked to find the pressure. So let's just use the same ideal gas equation. Again, noting that V3 is the same as V2, so that's been given. And we get that the pressure at 3 is 579.0 psia. All right, so now we have temperature and pressure at point 3. Now let's just move on from 3 to 4. So again, we have an isentropic compression process, expansion process from 3 to 4. So R, the compression ratio, is also equal to V4 over V3, which of course is VR4 over VR3. Okay. Well, again, we know R, VR3 we have from directly above, so we get the relative specific volume 6.571. And then lastly, we find our internal energy at this point. So one last trip into table A17E. And at VR4, we get U4 of 312.35 BTUs per pound mass. So now we have all of our thermodynamic properties that we need. Now it's just a matter of finding our terms. So if we want first to find the total work produced in BTUs, then the work that's produced during this power stroke is from 3 to 4. So the work from 3 to 4 is just the mass times the change in specific internal energy from 3 to 4. So that's 0.5084 BTUs. And then you're also asked to find the net work output. And that's just going to be the difference between the work out and the work in. So the work out from 3 to 4 we found directly above. The work in is just going to be the mass times U2 minus U1. So again, factor in the numbers. I get 0.3371 BTUs. And then lastly, you're asked to find the thermal efficiency, which is just going to be the net work over the heat input. There's many ways that we could do this, but let's also note that this is equal to the net work, which is above. And then the heat input is just the mass times the heat input per unit mass from 2 to 3. So U3 minus U2. Of course, this is already given, right? So it's not like we have to calculate it. We can just plug in the number. So plug in the numbers, and we end up with 0.489 or 48.9%. And there's your problem number 1. So this was not a trick problem. It was pretty straightforward as long as you understood how to solve it. Now let me note that I did tell you to solve using variable specific heats. So as such, you definitely want to use your relative specific volumes in this type of problem. You're not going to use equations that relate temperature and volume or temperature and pressure because that's the method of constant specific heats. I also note that Using variable specific heats, you have to use the ratio of work to heat input. You can't just use the equation 1 minus 1 over the compression ratio to the k minus 1 over k power, because that's, to k minus 1 power, because that's only applicable to constant specific heats. So this is correct. Now, I will note that there are some students that just entirely solved the problem using constant specific heats. There's other students that kind of went back and forth. For some parts of the problem, they use constant specific heats. For others, they use variable specific heats. All I can say is that I put notes down in red. I indicated how many points they took off, just so you know in general how much things were worth. First of all, just pulling the right value of R out of the tables would give you a point. 2 points for using the ideal gas equation to get V1, 2 more points to get R, 2 more points at T1 to get the data out of our table, and then another 3 points for knowing how to use the relative specific volume to find VR2 and ultimately the internal energy and temperature at 2. 2 more points for finding the pressure at 2. 3 points for using the heat input in order to get U3, and then another 2 points just to know what to do with U3 to get the temperature, and another 2 points to get the pressure. And then lastly here, 3 points for finding VR4, another 2 points, 3 points combined for finding VR4 and then getting the internal energy. And then basically 2 points for the work output, 3 points for the net work, 3 points for the thermal efficiency. So, you'll see little minus 1s, minus 2s, minus 3s, sometimes more, depending upon how far along you got in the problem. Anyway, if there's questions, you can certainly see me afterwards, but I've tried to indicate pretty clearly, what I took points off for. So are there any questions on problem number 1 then? Okay, then let's move on to number 2. And the exams are here, homework is there. So, and they're all alphabetical still. All right, so again, if there are no questions on number 1, oh, by the way, before I move on, I would just generally take a point off for any little error. If you have a math error, there's a point. If you pull the wrong data out of a table, there's a point. If your sign is wrong, there's a point. Conversion factors, there's a point if you don't have the right units. So, if you presented answers without any units, there's a point. So, some of you basically minus 1'd yourselves from an A down to a C just because you weren't as careful as you could have been. Really, if you got 3 or 4 minus 1s in every problem, and then the occasional little mistake here and there, then, it certainly would have affected your grade. Nonetheless, you'll see all these little minus 1s here and there. Also, if you did solve it using constant specific heats, I still gave you some partial credit. It just depends on how far along you got. It could be anywhere from minus 3 to minus 15. It just depends on how good you were in explaining what you were supposed to have done and how far along you got. So again, there's indication on your papers how many points I took off. So let's go on to number 2 now. And number 2 is a Brayton cycle problem. And on the Brayton cycle, we would generally start with a TS diagram. And on this one, because you're told that you have an intercooler and a reheater and a regenerator, then we have to include all of those. And of course, also keep in mind that it's a non-ideal compression process as well as expansion process. So we go from 1 to 2s, and here's 2. And then 3 is the same as 1. And 4s is the same as 2s, and 4a is the same as 2. We move through the regenerator to 0.5, through the combustion chamber to 0.6. And again, we have our expansion from 6 to 7s, and then 7a, and then 8 down to 9s, or 9a. And then as we move back through the regenerator, we'll come back down to state point 10. And then finally, we reject heat into the environment. So this is what our TS diagram should look like. And really, it's just a matter of figuring out how to find the various enthalpy terms, right? This is a Brayton cycle. So it turns out the problem-solving methodology is not really a whole lot different than it was for the Otto cycle, right? So we'll start at state point 1. Actually, before we do that, let's note that our pressure ratio is 1,050. That's the maximum over 100. That's the minimum pressure. So that's just 10.5. But also keep in mind that we need to find the pressure ratio for each stage of compression and each stage of expansion, and that's just the square root of the total pressure ratio, which is the square root of 10.5, so this is 3.240. So the pressure ratio per stage has to be found before you do anything else. Now we can begin. So we're given the minimum temperature, and that's T1 of 280 degrees Kelvin, I guess, right? So at T1, we're going to go into, well, air tables, right? So into table A17. And here we need to use relative pressures because it's pressure data that we're given along with our temperature data. So the relative pressure is used, and we find that the relative pressure is 1.0889, and the enthalpy is 280.13 kilojoules per kilogram. Okay. Now we would note that the pressure ratio is the ratio of the relative pressures for the isentropic process from 1 to 2s. So this would be the pressure ratio per stage, and well, again, we have that from above. We have PR1 from above. So we just plug them in, and we get PR at 2s of 3.528. Now that we have this, well, we can go into our table. So at PR2s, back into the air tables, and we can get the enthalpy at 2s, which is 292.35 kilojoules per kilogram. And now we have to use the compressor's isentropic efficiency. So that's just this equation. And everything is known except for the actual enthalpy leaving the compressor. So we get, oh, I'm sorry, this down here should say 392. And over here, this is 402.11. Yeah, so H2S is 392, and H2A is just a little bit higher than that. Let's also keep in mind that because of the nature of our intercooling, the temperature at 1 and 3 is the same, the temperature at 2 and 4 are the same, the enthalpies are the same. So we found H1, but this is also H3. We found H2A, but this is also the actual enthalpy at 0.4. So just keep that in mind. So we're actually done now with compression. There were some students that did this whole process a second time and ended up with exactly the same answers as we would expect, and there was really no need to do that. It wasn't wrong, nonetheless. So now we go on to the maximum. So 0.6 is our maximum. That's going to be, what, 1600 Kelvin? I think that's what I gave you in the problem. So again, we just go into our table, and we need PR6, and that's 791.2. And we need H6, which is 1757.57 kilojoules per kilogram. And now we're going to go through the expansion process. So the pressure ratio per stage is not just equal to the ratio of pressures, but also equal to the ratio of relative pressures. So this is PR6 over PR7s. So at 7s, the relative pressure is 244.20. And now that we have that relative pressure, you can go back in to get the enthalpy. And then we use the efficiency to get the actual enthalpy. So at PR7s, we get H7s. Not my day. Okay, so A17. So the enthalpy at 7s is found as 1286.52 kilojoules per kilogram. And then again, the compressor's efficiency. I'm sorry, I said compressor. This is not the right equation. This is the turbine efficiency. Same value, but for the turbine. Anyway, so this is the actual over the ideal. So H6 minus H7A over H6 minus H7S. So this is really what needs to be solved for. Anyway, the actual enthalpy of 0.7 comes from this, and this is 1324.2 kilojoules per kilogram. And again, we recognize that the conditions at the inlet and the exit of each turbine stage are the same. So H7A and H9A are the same. H6, which we found before, is also equal to H8. So now we have all of our enthalpies except for the one on the air side leaving the regenerator. So lastly, we have to find our regenerator. We have to use our regenerator effectiveness to get the enthalpy at 5. So keep in mind, this is the actual heat input through the regenerator, which is from 4A to 0.5, divided by the maximum possible heat input, which is where we would go from 4A all the way up to 9A. So H9A minus H4A. Anyway, everything is known. We find the enthalpy at 5 as 1185.89 kilojoules per kilogram. And now it's just a matter of finding all these various terms. So first we would note that the turbine work, at least on a per unit mass basis, is just twice the enthalpy change from 6 to 7A. And the compressor work is just twice the work due to the compression process from 1 to 2A, so H2A minus 1. So the turbine work is 866.74. And compressor work, 243.96, both in kilojoules per kilogram. The net work, of course, is just the difference between the two, which is 622.78 kilojoules per kilogram. We can calculate the back work ratio now. This is just the compressor work over the turbine work. So this is 0.281. Net work we've found. Okay. And now we need to find our heat input. Keep in mind that we have two heat inputs, right? One in the combustion chamber from 5 to 6, so H6 minus H5, but then also one within our reheater as we go from 7A to 8. Okay, so just make sure you include all these different terms, and we end up with 1005.05 kilojoules per kilogram. So there's our heat input. And then last but not least, the net work over the heat input can be found. That's our thermal efficiency. We get 0.62, or just 62%. And there you have the second problem. Okay. So as far as the grading goes on this one, 1 point for just finding the pressure ratio, and then 2 more points for using it properly to get the pressure ratio per stage. And then 3 points for going through the compression process from 1 to 2 using the appropriate relative pressures. 2 more points for using the compressor's efficiency to get the actual enthalpy at 0.2 and at 0.4. Similarly for the turbine, 2 points for using the relative pressures appropriately and ending up with H7S, and then 3 more points for using the isentropic efficiency. Reverse that. 3 points for using the data properly to get H7S, and then 2 points for using the turbine efficiency to get H7A. 3 points for the regenerator effectiveness to get the enthalpy. And then 1 point apiece for the turbine work, the compression work, and 1 point as well for the net work. 2 points for knowing what to do with the work terms to get the back work ratio, 3 points for the heat input, 2 points for the thermal efficiency. So, if you missed little parts of that, once again, I would have put little -1s, 2s, or 3s, or whatever. Again, if you didn't solve using variable specific heats, I didn't just put a big X through the problem. I just simply took off some points, consistent with how much of that you did get correctly. How much of the variable specific heat method you did indeed use. Anyway, are there any questions then on the second problem? All right. So for those of you who are coming in late, hopefully you picked up your exam now. Out of 60, the average was 42. The median score was 45.5. The range was between 8 and 60. about. 54 is 90%, so that's an A, 48 is a B, 42 is a C, et cetera, et cetera. So again, any questions on any of this? Great. Then we will move on. So first, a few homework problems from chapter 12. Okay, so this is your homework for the entire week. Okay. So today we begin a new topic, and this new topic deals with thermodynamic property relations. This is totally different than anything we've seen up until this point. The material that we're covering this week will not be used again after this week. We're just going to move on to new material. In fact, we're going to find that that's the case really for the next month and a half or so. We'll just be covering different topics, different items, and in general, we'll be using them and then just leaving them behind. So we're starting to learn a bunch of different things. With regards to thermodynamic property relations, there are problems associated with the thermodynamic property data that we have, and it's through this section on thermal property relations that we'll be able to rectify that problem. I suppose the question is, well, what is the problem that I'm talking about? And that is, how do we create tables of thermodynamic property data when we can't measure the majority of the property data that we need? Right? We don't have any kind of internal energy meters or enthalpy meters or entropy meters or anything like that, right? We can measure temperature, we can measure pressure, we can measure volume and mass, in other words, specific volume or density, but that's it, right? There's no other data that we can obtain. Yet somehow we've generated tables that include internal energy and enthalpy, et cetera, and et cetera. Well, where do those tables come from? That's what thermodynamic property relations are all about. Okay, we're able to take these general mathematical expressions and apply them to the research world, as apply them to data that we'll collect in a laboratory, and actually create the thermodynamic property tables that we now know we absolutely need in order to solve problems. So that's just your brief intro into thermodynamic property relations. And I got to figure out where I am. So much of what we're going to do today is just develop the general equations that are going to be utilized. And then when we continue this material for the rest of the week, then we're going to apply these equations in various ways to actually get the thermodynamic property data that could be used in tables. So again, this is called thermodynamic property relations. Okay, and this is the material that's in chapter 12. Right. So again, we understand that temperature, pressure, volume, mass are measurable, but we need things like internal energy, entropy, enthalpy, even specific heats, right? Cp, Cv. These are all thermodynamic properties that we have to come up with somehow. So let's just begin with some general mathematical relationships. Okay. So let's say we have a continuous function z, where z is actually going to be a function of two other variables. Let's just call them x and y. Okay. Now, as we're thinking about this, can anybody think of what kind of functions we might be talking about here? How about thermodynamic properties, right? We know that if we know any two independent intensive properties, then that's all we need, and we can find all the rest. So isn't that just a statement of the thermodynamic properties, that any one property is simply a function of any two other, again, intensive independent thermodynamic properties? Okay. So this specifically applies to our thermodynamic properties. Okay. So again, it's just worth a note that x, y, and z are independent intensive properties. Okay, so just something worth noting. Now, how do we handle a continuous function like this mathematically? Well, first let's put it into differential form. And we'll note that dz is actually related to the partial derivatives. So dz is the same as del z del xy dx. In other words, a partial of z with respect to x holding y constant dx, and then plus the partial of z with respect to y holding x constant dy. Okay. So this is simply a mathematical statement. We can call this the total differential. Okay. Now, what I can do is I can change this a little bit. I'm going to let this first partial term be simply called m, and this second partial term n. So basically dz is equal to m dx plus n dy. Okay? And this particular equation, I'm just going to call equation A. We are going to use it quite a bit. Okay. So this is one equation that's of interest to us. And we'll note, again, where m and n are the partials. M is a partial of z with respect to x, holding y constant. And n is the partial of z with respect to y, holding x constant. So again, this is just mathematics. I'm sure that when you were taking your, what was this, Math 214 class, you probably expected that eventually you're going to have to use all this material on partial derivatives, and indeed the time is upon us. So if you're not comfortable with partial differential calculus, you're going to have a little bit of trouble this week. I might just suggest read the book, make sure you follow along, and I'll try to make this as understandable as possible. Nonetheless, these are the partials, and these two equations for m and n I'm just going to call equation B. Okay. So again, we understand that we're really dealing with thermodynamic properties here and relationships between thermodynamic properties. So let's just continue. So we would note that A and B, these equations, are going to apply to any thermodynamic property as long as they're independent and intensive. A couple of other things to note. And again, this is really just review from a math class that you may not have taken for 2 or 3 years. One thing that we would note is that we're often interested in second partials. So the second partial of z with respect to x and y is also equal to the second partial of z with respect to y and x. So again, this is something that we've used before. And this can actually be rewritten in terms of m and n over there. So for instance, another way of rewriting this second partial derivative is just del by del y of del z del x y holding x constant. So this is just another way of writing that. And then over here, this is going to be del x. Oh, you know what? One of my brackets is in the wrong place. This one. Okay, so if you just move that left bracket out. And in fact, I have the wrong bracket here too. Okay. So anyway, del by del x of del z del y holding x constant, holding y constant. Okay, so this is, again, just something that hopefully we remember from our mathematics class. But please note again that this term right here should be m, which it is. And this term right here is n. So therefore, we could just rewrite this, and we'll write del m del y x equals del n del x y. So here's another equation that really just comes right from our partial differential calculus. And this too is an equation that I'm going to use on a regular basis. So I want to call this one equation C. Okay. And then there's actually one other equation that's going to be quite useful to us that we'll be using over the next couple of days. So let me just call this another note. There's a relationship that was called the cyclic relation. So let me just spell it out for you. Basically, if we have the partial of x with respect to y holding z constant, and then multiply by the partial of y with respect to z holding x constant, and then the partial of z with respect to x holding y constant. If we were to multiply these three partials together, then this actually equals -1. So here's another equation that we're going to utilize. And this one I want to call equation D. Okay. So the question now is, what do we do with these? It's not at all clear at this point. I mean, we know that we have different relationships that compare different thermodynamic properties, that we know, but we still don't know exactly what to do with them. And again, keep in mind during all of this that ultimately we're really trying to find relationships between the properties that are measurable and the properties that are not measurable. So with this all in mind, let's develop the first set of equations, which are called the Maxwell equations, or Maxwell relations. Okay, so everything else up until now has really just been review of your partial differential calculus, right? There's nothing really new up here. There's just equations. Now we have to figure out what to do with them. So what is our goal? Okay, it's actually not that hard. What we're trying to do is we're trying to find thermodynamic equations that are in the form of equation A. And if we have an equation that's in the form of A, then we can very easily rewrite that in the forms of B or C or D. And hopefully in doing so, we end up with exactly what we want, which is some sort of relationship between the measurable and the not measurable properties. So we actually have two equations that are of the form of equation A that we've already seen. So before I even do this, let me just note, we need to find equations in the form of equation A, and then use B, C, and D. Well, we're not going to use them all at once, by the way, but we could use either equations B, C, or D to find the relationships between the various properties. So we need to find equations in the form of A, and then use B, C, and D to get relationships between measurable and not measurable properties. Okay. So again, just to make sure we know where we're headed, what are these equations that I alluded to earlier, equations in the form of A that we already have seen? Well, these were first explained to you back in Chapter 7 in your first course in Thermo. These were called the TDS relationships. These are also rewritten here in Chapter 12. So the TDS relationships are two such equations. So one of them was written this way, du equals TDS minus PdV. Please note that these are all lowercase. These are all intensive properties. Specific internal energy, specific entropy, specific volume, and of course pressure and temperature are intensive. So that's one of the equations. This one I'll call equation 1. And then the other TDS relationship is this one, dH equals TDS plus V dp. So this is the second TdS relationship. So from these two equations, I can apply B, C, and D to develop other equations of interest to me. All right, so this is fine. We'll get back to that in a few minutes. There's two others that we also find useful. So two other equations to derive. Now, in order to derive these two additional equations, the first thing I need to do is I need to invent some more thermodynamic properties. Now, we've already seen some thermodynamic properties invented for us, right? I mean, enthalpy is probably the best one to show as an example. By definition, U plus PV is called enthalpy. How about the specific heats, right? Cp and Cv. Cp is a partial of U with respect to T holding V constant. So it's a relationship between one property and other properties. Cp the same, right? Cp is defined as a partial of H with respect to T holding P constant. So we've already seen how one thermodynamic property can actually be invented, if you will, based on mathematical relationships with other properties, and that's exactly what I'm going to do here. So the first equation is called the Helmholtz function. And the Helmholtz function is just A. And A is simply defined as U minus Ts. Okay. So this is the first equation. Now I need to get that in the same form as equations 1 and 2. In other words, I need to put them in the form of equation A. So let's just take a derivative. So dA is going to equal, well, du. And then here we have to use the chain rule, right? So this is going to be minus TdS and then minus SDT. So minus TdS minus SDT. Okay, so that's how we take a derivative of this type. And then what I want to do is I want to plug in equation 1 into here. After all, du minus TdS is going to equal minus PdV. So we get dA is going to equal minus PdV and then minus SDT. What do you know? That's exactly what we're looking for, right? It's in the same form as equation 1, equation 2, in other words, in the form of equation A. So I'm going to call this one equation 3. So there's another relationship that's in the form of equation A. Now, again, it was derived using this new thermodynamic property called the Helmholtz function, but you'll see that it does simplify down to an equation in the right form. Again, we don't know how we're going to use these equations. At this point, I'm just deriving the equations, and then we'll get to how to use them here in just a little bit. All right, another equation that's derived is derived from what's called the Gibbs function. And the Gibbs function is just given the lowercase letter g. And by definition, the Gibbs function is actually similar to the Helmholtz function. It's actually h minus t times s. So again, I need to put this into differential form. So dg equals dh. And then again, using our chain rule, so this is going to be minus tds minus sdt. Okay. And now what I want to do is I want to plug in 2. Right? So dH minus TdS is going to equal VdP. So therefore, dg is equal to VdP minus SDT. So there's another equation. And this will be the fourth equation, so I'll call this equation 4. Okay. So now what we have are 4 equations that are all in the same form as equation A. So 1 through 4 are in the form of A. So let's just use equation B now with those 4 equations to write some new equations. So 1 through 4 in the form of equation A. Therefore, we can use B for each one to get the following. Okay, so I've just erased the equation B. So now what you should do is you should just go back into your notes and compare. Oh, I'm sorry. I wrote equation B. That's not right. We want to use equation C here. So this is my mistake. Anyway, you want to compare the equation in the form of A to the equation C that's over here. So again, please correct that. I should have said C and I said B, and that's not right. Okay. So let's just do it one by one. And we'll start from equation 1. All right. So again, it's just a matter of making sure each term lines up properly. So from equation 1, we would actually get del T del Vs. Okay, so that comes from this. You know, x is the same as s, and y is the same as v. And, well, m is the same as t. So we get del T del Vs, and this is going to equal the negative of, and now again we have to look at the individual terms. So, you know, here we're comparing x and y and n. So we get minus del P del S V. Okay, so this is the first equation. Now, this is called one of the Maxwell relations. There's actually 4 Maxwell relations, and that's what this whole topic was called, right? Maxwell relations. So what I'm going to do is I'm just going to call this M1. I'm going to have to call it something. So M1 just means the first Maxwell relation. So there's the first one. Now we're going to do the same thing again for the second and the third and the fourth numbered equation. So now we'll go to equation 2. And we end up with something that's very similar. We have del T del Ps is going to equal del V del Sp. So again, this is of the form of equation A. We're just rewriting it using its components, x and y and m. So we get this equation. So this is my second Maxwell relation. So I'll just call this one M2. By the way, the author doesn't call it M1, M2, whatever. It just calls them equations 1216 through 1219. I mean, that's just the order that those equations are presented in your textbook. But I'm just going to refer to them as the first or second or whatever Maxwell relation. So M1, M2, etc. Now, let's go to the third equation. And that was the one based on our Helmholtz function. And again, we're just going to write it in the same way. So this one is going to be del S del V T equals del P del T V. All right, so this one will be our third Maxwell relation. And then last but not least, from our Gibbs function equation, we end up with del S del PT equals minus del V del T P. So this is the fourth Maxwell relation. So these 4 equations are equations that we're going to use on a very, very regular basis. Okay. So if you feel like underlining them, you certainly can, because we are going to use them a lot. So I do want to go through an example problem. I mean, quite frankly, we do have the relationships necessary to start doing some problems. I will note that since we're specifically talking about continuous functions where one variable is a function of 2 other variables, we're also specifically talking about our simple compressible systems, right? We're not dealing with any chemical reactions. We're not dealing with any electrical work or magnetic effects or anything like that. No surface tension forces. I mean, none of those forces are going to be included here. So we're still dealing with a simple compressible system. Nonetheless, we now have 4 relationships that we can utilize. And believe it or not, these are the types of relationships that we would utilize when we're dealing with, well, creating thermodynamic property tables. So let me just go through an example problem. And this is actually similar to one of your homework problems. So here's the example. What I basically want to do is just verify the validity of one of the Maxwell relations. So verify the validity of M4, the fourth Maxwell relationship. And let's do it for a particular substance. How about the refrigerant 134A? And we'll do this at a particular temperature and pressure, so at 80 degrees C and 1200 kilopascals. Okay. So the first thing that I would like to do is just simply write down this particular relationship. The fourth Maxwell is del S, well, it's right here, del S del PT equals minus del V del T P. Okay. Now, here's where things get a little bit strange. We have to imagine ourselves in a laboratory somewhere, okay? Don't think of yourself as being in a classroom or studying at home. We're in a laboratory somewhere, and we've just collected a variety of thermodynamic property data based on properties that we can measure, right? Like temperature and pressure. And what we're trying to do is find a relationship between these measurable properties and entropy. I mean, entropy is the one variable in all four of these Maxwell relations that is not measurable. So somehow, using these four relationships, we should be able to come up with at least entropy data for the thermodynamic property tables. So don't think of your thermodynamic property data as data from a table. Think about it as if you were actually taking this data yourself in a laboratory somewhere, okay? And you had data at 80 degrees and 120, and we're going to see if the thermodynamic property tables are accurate. So that's what we're going to do here. Now, this particular type of analysis is often called bounding analysis for reasons that you'll see here in just a minute. So this is called bounding analysis. Okay. So the first thing we do is we would note that in our laboratory situation, we're not actually going to be looking at partial differential data. We're just going to be looking at data, temperature data, pressure data, volume data, whatever. So the first thing we want to do is we want to approximate this equation as follows. So we approximate as follows. So instead of del S del P, I'm going to write it as delta S over delta P at a particular temperature equals the negative of delta V over delta T at a particular pressure. So this is actually the equation that we're going to analyze. So we need to go into our property tables and essentially bound our given data. Okay. Now we know that at 80 degrees C, 1200 kilopascals for this refrigerant, this is actually going to be in superheat region. So go to A13, which is your superheat tables. And basically what you're going to do is you're going to read the data that bounds this particular data point. So let me explain. So let's say that we have my pressure of 1200 kilopascals, and we have our temperature of 80 degrees C. So it's this number right here in the middle that we're really interested in. And that's the number we're trying to prove is accurate or not. And what I want to do is bound this. So what I want to do is go into my table A13, my superheat tables, and I would note that at one lower pressure table, we're down to 1,000 kilopascals, and at the next higher pressure, let's say, entry in the table, you know, the superheat tables are a series of subtables, right? So we've got the 1,200 kilopascal subtable. The one at a lower pressure is at 1,000. And the one that's a little bit higher is at 1,400 kilopascals. And then the temperature data that bounds 80 degrees Celsius is actually at 70 and 90 degrees Celsius. Okay. So what we're going to do is we're going to look at all this bounding data. We're going to look at the data over here and over here and over here and over here. And somehow, by using the equations that we've just talked about, which is approximated as this, I should be able to see whether the Maxwell relations work or not. Now, really, what you'd be doing if this were a real lab is you'd just be recording pressure and temperature and specific volume data, and the end result would be to find your entropy data. I mean, that's really what we'd be looking for. But right now, we're just trying to use this bounding analysis in order to validate one particular Maxwell relation, which is just this one, approximated as this one. So with this all in mind, and again, that's just a little figure that'll help you, hopefully help you understand this material. So let's now go into table A13. And pull the numbers out that we're going to need. Now, let me rewrite that delta equation first. Okay. So instead of delta S, why don't I just write this as S at 1,400 kilopascals and 80 degrees C, and then minus S at 1,000 kilopascals and 80 degrees C. So there's the numerator, right? So this is the entropy change as it is affected by pressure at a particular temperature, right? So it says at the constant temperature of 80 degrees C. And then in the denominator is just the delta P term. So this is just going to be 1,400 kilopascals minus 1,000 kilopascals. So there's the left-hand side of the equation. And now let's look at the right-hand side of the equation. So here we have the specific volume. Now please note that this is a specific volume that's going to be at the bounding temperatures, right? We're changing specific volume with respect to temperature at a given pressure. So this will be the specific volume at 90 degrees Celsius, but also at 1,400 kilopascals minus the specific volume at 70 degrees Celsius, corresponding to 1,400 kilopascals. Oh, I'm sorry, 1,200 kilopascals, right? 14 and 1,000 are the bounds. This is my data at 1,200. So this should say 1,200. Okay. And this is delta V over delta T. So basically, this is just 90 minus 70. And these are both going to be in degrees Celsius. But it is a temperature difference, right? So a temperature difference in Celsius is the same as a temperature difference in Kelvin. So I'll just leave it in Kelvin. And we don't want to forget our minus sign. So now let's just go into our tables and pull the data out. I mean, after all, this equation is just an approximate form of the fourth Maxwell relation. So we go into our tables now. Now let's actually pull out data. So at 1,200 kilopascals, 80 degrees Celsius. So basically that's the data that's over on the far right-hand side of the diagram. The entropy is 1.0056. And this is going to be in kilojoules per kilogram per Kelvin. And then the entropy at 1,080 degrees Celsius. This is 1.0459 kilojoules per kilogram per Kelvin. So those are the entry terms in the numerator. And then in the denominator, well, this is just 400 kilopascals. And then on the right-hand side, we have our minus. And now we go back into our tables again, and we look up the specific volume at 90 degrees Celsius, 1,200 kilopascals. And that's going to be 0.021506 cubic meters per kilogram. And then at 70 degrees Celsius, but at the same 1,200 kilopascal pressure, this is 0.019502 meters cubed per kilogram. And then we divide that again by 90 minus 70, which is 20 Kelvin. Now, it would appear that our units don't really work out properly, but they actually do, right? A kilopascal is the same thing as a kilonewton per square meter, and a kilojoule is a kilonewton meter. And then you'll see that all the units cancel out appropriately. So now let's go through the mathematics, and we end up with minus 1.005 times 10 to the minus 4th, and the units are going to be meters cubed per kilogram per Kelvin. And on the right-hand side, we have minus 1.002 times 10 to the minus 4th meters cubed per kilogram per Kelvin. Okay. So this essentially validates the fourth of the Maxwell relations. Keep in mind that while the two numbers are not absolutely identical, they're certainly very, very close. I mean, we're only off by 3 parts out of 1,000. So, I mean, we're accurate to within a fraction of a percent. So that's actually very, very good. So we have indeed validated the Maxwell relation. Okay. Now, again, if you want it to be even more accurate, then we're going to have to reduce our bounds. I mean, in a laboratory situation, we're not only going to have data in 200 kilopascal increments or 10 degrees Celsius increments. We're going to try to get as tight as we can. You know, we're going to try to go maybe by 1 kilopascal at a time for our pressure data, and, you know, maybe 1 or even a tenth of a degree Celsius on our temperature data. And our data is going to get a lot closer in to the center, and thus when we do our bounding analysis, we'll get more accurate results. But still, even using the data that's in the textbook, we're at least able to prove that, yes, the Maxwell relation is indeed valid just based on this bounding analysis. So let me give you a little more time to think about this. I'm done for the day, and we're out of time anyway. But certainly before Wednesday, you want to read your textbook. Make sure you look at this type of analysis. There is an example problem, example 12-4 in your textbook, that is very similar to this. There's a homework problem, 12